Here we've got a similar situation to one we had before, where we've got two particles connected by a string that passes over a frictionless pulley. The string is inextensible, but this time we're going to assume that there is friction between this particle and the table. And there's something called the coefficient of friction, which is going to be 0.4. Now the coefficient of friction depends on the nature of the table and the particle. Questions at A level will either tell you the coefficient of friction or they'll ask you to work it out using some maths. So what forces are operating here? Well, obviously there's a weight here, which is 7G. There's a tension in the string. There's the same tension there. Got a weight here, 5G. We've got a normal reaction, which we'll call R. And then there's going to be friction, because the friction is going to oppose the motion. And the basic equation that we need to use is that the frictional force is always less than or equal to the coefficient of friction multiplied by the normal reaction. Now, if the whole system is just on the point of moving, then F equals mu R. It's never possible for F, the frictional force, to be greater than mu R. It doesn't start pulling particles backwards. But if the whole system is just on the point of moving, then F equals mu R. Clearly the system is going to be moving in this direction here. Let's call this acceleration A, and let's see what equations we've got. We've certainly got F equals mu R. So this becomes F equals 0.4 times R. If we resolve the 5 kilogram forces vertically, then 5G equals R. Let's call this equation 2. This was equation 1. Let's consider F equals MA on the 7 kilogram weight, then 7G minus T, that's the force, that's the resultant force, is the mass 7 times the acceleration. And let's consider F equals MA on the 5 kilogram weight, then it's T minus F, that's the resultant force, that's the mass times the acceleration. So we've got 4 simultaneous equations to solve. So let's write those out again. So here are the 4 equations. It's very easy to get this in a complete mess because solving 4 simultaneous equations can be a little bit tricky. So it's very important you write down what you're doing. So let's put equations 2 and 1 together. Instead of writing R, I can write 5G. So I get F equals 0.4 multiplied by 5G. 0.4 times 5 is 2, so that means F equals 2G. And that we're going to call equation 5. I can now put equation 5 into equation 4. And I'm going to get T minus F, but F is 2G. That equals 5A. And let's call that equation 6. So what equations haven't I used yet? I've used that one, I've used that one, and I've used this one, but I haven't yet used 3. So let's use equation 3 and equation 6. So if I add equations 3 and 6, I'm going to get 7G minus T plus T minus 2G. So the minus T and the plus T are going to cancel out. So I'm going to get 5G equals 7A plus 5A, that's 12A. So that means that A equals 5G over 12. I can now put that into equation 6. So equation 6 says T equals 5A plus 2G. That's here. Add 2G to both sides. 5A plus 2G, so that's 25G over 12 plus 2G which is 49g over 12. I can now use equation 4 to work out what f is. So I know what t is, that's here. I know what a is. Here's equation 4. So I can say that if I add f to both sides and take 5a from both sides, I get t minus 5a equals f. So therefore f is 49g over 12 minus 5a. It's not a, it's g, isn't it? So it's 49g over 12 minus 25g over 12, that's 24g over 12, which is 2g. So I now know what f is. And then if you remember, f equals mu r, and r is 0.4, so f equals 0.4 times r, so therefore r equals f over 0.4, which is 2g over 0.4, which is 5g. So now we've got all the solutions, let's write them out here. We've got f equals 2g and r equals 5g. So these are our final solutions to this problem.